Good afternoon, my name is Francisco Aquino, and this is my exam validation video. So for our first item, and this is from sections 3.1 to 3.6, given a function, we want to find the equation of the tangent line. What makes this problem different is that we also want the x values for which the function's graph would have horizontal tangent lines. And our given function here is x plus 2 times sine x. X plus 2 times sine x. So I first approached this problem by finding the derivative, because the derivative of a function represents the instantaneous rate of change at a single point for that function. And that is the slope of the tangent line. So we need to find the derivative. So I will go down here. Here's my work. Now, the reason why I took these steps is because, the derivative of x is just 1 from the power rule, because that x by itself is an implied single power. And then the 2 times sine x, that's a twofold derivative. The 2, that's a constant, so you pull that out using that constant rule. And then sine, the derivative of sine is just cosine x. And then there's your derivative. Finding it was pretty easy. Now here's the tricky part. You want to find the points on the graph, the x values, which have the horizontal line of tangency. Horizontal lines of tangency. And so, as we know, horizontal tangent lines have a slope of 0 or no slope. So what you want to do for that is set your derivative equal to 0 and then solve. Solve for x. And so here you can see that you can accomplish that down here, just some simple algebra, moving some numbers from the left to the right side, doing some division. And actually, down here, the solution goes into a little bit of trigonometry with the 2 pi k, where k is any integer, because this is dealing with the unit circle. And you want the angles, which the cosine of x is -1/2, which are angles that are part of the pi over 3 family. 2 pi over 3 here, and 4 pi over 3, with both of these having the plus 2 pi k term attached to them. And so after you do the work, these are the values that where the graph of f of x has horizontal tangent lines. These values end up multiples other versions like it, like if you change the constant. Okay. Actually, I'm going to go down here real quick and show my graph, just for proof of my work. For part B, here we have the original function, have its derivative, and then we have my work in green to verify that they're the same. Then you have those 2 points, and you can see the tangent lines where they touch and move. Now I'm going to go up and address the questions in the background. So for both the question and the background, the person is asking, is the exercise looking for the x values of which the graph of f would have horizontal tangents? And yes, that is what it's looking for. It's stated in the problem statement. And now to zoom in on the background, this person says that to take the derivative of 2 sine of x, they used the product rule. Now that's incorrect, because the product rule, which is the derivative of f of x times g of x, where f and g are 2 functions, that's basically where you're taking the derivative of g times f times g prime, and then adding it to the derivative of f times g. It's a sum of the 2 functions without the derivatives and the derivatives. And you can't do that with 2 sine x, because 2 is a constant and sine is just a function by itself. There's only one function. So that's where the constant rule comes into play with the trigonometric derivative rule for sine. And now, for your other question, after finding the derivative, how would you go about solving the horizontal tangent without a point? Well, here's the difference. When you're given a point, it's because you want to find the equation of the tangent line at that specific point for the original function. That's where that given point in the slope-intercept form of the equation comes in. But this problem is different in that it's just asking for the x values, which when you graph that function would create a horizontal tangent line. That's where the two problems are different. And it's a good question to ask because tangent lines and functions are very important. They represent rates of change and all that stuff. So I hope I answered your question. Now I'm going to move on to my second item. For this second item, which is from section 2.2.3, I believe, where it wants us to analyze the behavior and continuity of functions using limits. Now for this problem, we're given the limit as x approaches infinity of 1 minus e to the x over 1 plus 2 times e to the x. And so for this problem, direct substitution didn't really make sense to me to use because that would only work if you had like a whole number, like in the case of L'Hopital's rule, which is in section 4.4. So the fact that we're given this infinity made me think of this problem in terms of analyzing a function at infinity, like what's happening to the x and y points on the graph, the numerator and the denominator. So after looking at it, I found that there's a common denominator of 1 over e to the x, which you can multiply both sides in to simplify it. And after doing that work, you would get this nice function over here. And now what's happening at infinity is that e to the very large number, like you have e to the x, and these inputs, they keep getting larger and larger. And so you're having 1 divided by these increasingly large numbers. And eventually, the outputs from that, after they're subtracted from the number on the numerator and added by the denominator, you're going to get smaller and smaller numbers, increasingly getting larger and larger negative numbers, smaller, until you eventually reach 0. That's what's happening with the graph as you go to infinity. And now I'm going to go up and address the questions and the background information. Question 10. Understanding limits is question 10. How can you determine the equations of horizontal asymptotes for the function in this exercise? To give an honest answer, the best way to do that would be to plot the function in Desmos and look to see where both of the ends of the graph move out toward. Because with horizontal asymptotes, it's a horizontal boundary that the two ends of the graph, they move parallel with but never touch. And that will be the equation of the form y equals that number. So you can just graph that on Desmos to find that out. Now down here with question 11, where it says, is there a way to use algebra like in section 2.6 to find the limit? For this one, I mean, yeah, you can use algebra. You look for a common denominator, multiply, and cancel out the terms, that stuff. So I see that we kind of got the similar answers here, but there are two crucial problems. One, your horizontal asymptote is not 1/2. Furthermore, that number is supposed to be negative because of what's going on with the function at infinity for the numerator and the denominator. That's going to be a negative number, negative 1/2 for your limit. Because again, with this, you're looking for the limit. And also for the horizontal asymptotes, again, you can just graph those on Desmos and plot them using the y equals whatever number that is. Now to address the reason. But yeah, I'll go down here and illustrate. Actually, even though I didn't show it here, if you approach the graph from the left and the right, their outputs will converge to negative 1/2. That is numbers that are close to negative 1/2, but slightly smaller, and the numbers that are closer to 1/2, but slightly larger on the right side. So that's it for my second item. I'm going to go on to my third and final item. Here we have the third and final item, item 8, competency 3, where it wants us to compute the derivatives for functions using everything we've learned, differentiation rules, techniques, things like that. So right away we have the function y equals x raised to the sine x. And when you look at this function, it's not like a power function or an exponential function. It's a strange one. So before you even get into the algebra parts, you want to manipulate this function so that way it's in a form that makes it easier to solve. So one way to do that would be to take the natural log of both sides, and you would get ln of y equals the ln of x sine x. Then you can just bring that sine x down times the ln of the x, using that rule from algebra. Now over here, to address the question, I remember doing this in class as well, and I could see where you got stuck. After you've taken the natural log to bring the exponent down, you can use the product rule, because here sine x and ln of x are functions, and so according to the product rule, it would go something like this. You'd have the ln of y is equal to sine of x times the derivative of ln of x, and then plus the derivative of sine x times ln of x. And so if you followed that through, you would end up with a situation kind of something like this, but where the derivative of ln of y, you need to use implicit differentiation, because that's also part of this problem. That's what you forgot to use. If you had used implicit differentiation using the derivative rules, you would have gotten ln of y turns into ln of 1/2 of 1 over y with a factor of y prime, or dy dx, depending on whatever notation you want to use. And that's important because to solve this problem, you would have ended up with a situation where you want to multiply both sides by y to cancel out this here, this y here. And you would end up having y equals ln of x cosine x plus sine x times 1 over x. And that's important because the implicit differentiation here, this, it basically means you already have y prime after multiplying the y to get rid of the 1y fraction. And so what other y would remain here? Because there's also a y here on the right side. What y is that? That y is your original function. And so you plug that in. And what this means is that for the derivative, the original function isn't specifically a part of it, but it's related in some way. So yeah. And here, we'll just show my work real quickly and see what I was talking about. So yeah. That concludes my exam validation video. Hope you have a good evening. I'll see you next time.